So yes, a lot has been going on lately, and in between work and different topics and subjects that I see online. Like, I wanted to pick up just one thing today because I don't know when is the next time I'll have like the whole afternoon free. So I want to talk about four rocky planets smaller than Earth that were discovered around a Barnard star, which is only 6 light years away. Then came the detection of a rapidly disintegrating planet of the size of Mercury that orbits very close to its star every 30.5 hours, as well as the finding of a super-Earth exoplanet HD 2794d situated in the habitable zone of a G-type star approximately 19.7 light years away. Yes, so K2-18b was my choice for today, and the red dwarf star K2-18, which is situated in the constellation Leo, around 124 light years away from Earth, is orbited by the super-Earth exoplanet K2-18b. Using the transit method, the Kepler Space Telescope made a discovery in 2015. However, it was only recently discovered that DMS is present. No, it's not DMT, come on. And as far as I'm aware, it's not hallucinogenic. Dimethyl sulfate, or DMS, was just recently examined and potentially detected in the atmosphere of K2-18b using data from the James Webb Satellite Telescope, or JWST, as opposed to K12-18b, which was discovered by the Kepler Satellite Telescope. And I always say, time is everything. Even better, timing is everything. And I always say that time, apparently a completely anthropocentric concept, is one thing we have no control over. This wasn't about looking for another technological civilization, but still it is worth mentioning. Due to self-destructive risks like nuclear war, environmental collapse, or technical hazards, many futurologists and researchers predict that technological civilizations typically only last a few hundred to a few thousand years before disintegrating or changing. And in terms of cosmic timescales, for example, estimation place the average civilization lifetime on the order of years to millennia. The vast distances between stars, often thousands of light years, means that transmissions take centuries or even millennia to reach other civilizations, if any. And according to Sebastian von Horner, two-way communication with a civilization's lifetime is implausible because the average distance between civilizations in the Milky Way is roughly 1,000 light years, and the likelihood of meaningful contact is significantly diminished by the great distance between civilizations and their limited lifespans. Assumptions regarding extraterrestrial signals, such as radio frequencies and intentional transmissions, and a constrained observation window are the foundation of our current detection techniques. According to futurologists and scholars, a technological civilization's anticipated survival duration might range from decades to millennia, again, with the majority of models highlighting the high probability of self-destruction. Surprise, surprise, why I'm not surprised. Short-term estimates decades to centuries. Biotechnology and AI risks models factoring in dual-use technologies. Advanced bioweapons AI predict median survival times of decades to centuries for human civilization. And, for example, widespread access to lethal biotechnology could collapse civilizations within 200 years. What is a statistical forecast like? Using the Copernican principle, so we are assuming we're not special in time, humanity's technological lifespan is statistically likely to endure a few centuries, but not much longer given current existential threats. And medium-term projections, centuries to millennia, like if we have to also mention Kardashev scale transitions, let's say futurists like Michio Kaku, he estimates that there's 100 to 200 years to reach Type 1 status if we harness planetary energy, and a few thousand years for Type 2 or stellar scale energy. However, exponential growth is constrained by natural limits and self-destruction risks like nuclear war, climate collapse, and so on. Now it completely changed the direction of this of this discussion. But like what we were talking about, let's talk about our key characteristics of actually of K218b. So his mass is approximately 8.6 to 8.9 times that of Earth. Radius is about 2.6 times Earth radius, placing it in a sub-Neptune or super-Earth category. The orbital period is roughly 33 days, orbiting within the habitable zone of its star. Orbital distance is around 0.14 to 0.16 AUs from its host star, and surface temperature is estimated like -8 Celsius, suggesting conditions potentially suitable for liquid water. And that's pretty much it. The atmosphere is K218b is notable for being one of the first exoplanets in the habitable zone with a characterized atmosphere. And observations by the Hubble Space Telescope initially detected water vapor in its atmosphere, while more recent studies using the James Webb Space Telescope revealed the presence of methane and carbon dioxide and possible biosignature molecule called dimethyl sulfide or DMS. So yes, these atmospheric components suggest K218b could be a so-called an ocean covered planet with a hydrogen-rich atmosphere, which might be conducive to life. And the detection of DMS is particularly intriguing because on Earth it is produced exclusively by microbial life, though confirmation of biological activity on K218b remains like in the air, and requires further study. And also, K218 also hosts a second non-transiting planet, K218c, which is a Neptune-like and orbits closer to the star. We've been actively observed the skies for the Earth-like planets since probably Giordano Bruno in the late 16th century, who proposed that stars are like the Sun and likely have planets orbiting them. Isaac Newton also speculated in the 18th century that fixed stars might be centers of planetary systems similar to ours, and for a long time these ideas remained theoretical and were explored mainly through philosophy and science fiction rather than empirical science. In the 20th century, astronomers made various claims of exoplanet detections, which were later discredited. And the first confirmed detection of exoplanets came in 1992 with the discovery of two terrestrial mass planets orbiting a pulsar, PSR B1257+12, by Alexander Volschan and Dale Frail. The first confirmed exoplanet orbiting a main sequence star was found in 1995, a giant planet orbiting 51 Pegasi, and early detection methods included radial velocity measuring star wobble due to gravitational pull of planets, and transit photometry, which is detecting dips in starlight as planets pass in front. The first transit observation of an exoplanet H2 29458b was made in 1999. The French CORT mission, launched in 2006, was among the first space missions designed to detect transiting exoplanets capable of finding planets several times larger than Earth. NASA's Kepler Space Telescope, launched in 2009, revolutionized the search by monitoring over 100,000 stars for Earth-sized planets in habitable zones, greatly increasing the number of known candidates and confirmed planets. Kepler identified thousands of exoplanet candidates, including many Earth-sized and super-Earth-sized planets, some within their stars' habitable zones. And in 2013, several Kepler candidates less than 1.5 Earth-ready were confirmed in habitable zone. The first near-Earth-sized planet orbiting a Sun-like star, Kepler 45-2b, was announced in 2015. The Transiting Exoplanet Survey satellite tests, launched in 2018, continued this search and discovered TOI 700d in 2020, the first Earth-sized planet in the habitable zone detected by tests. In 2023, NASA's James Webb Telescope detected LHS 475b, an Earth-like exoplanet, marking a new era of detailed study of such worlds. Microlensing has been used to detect smaller, cooler planets far from their stars, such as Ogli 2005, BLG 390, LB, a rocky planet about 5 times the size of Earth, discovered in 2005. And the Cassini-Huygens mission from 2004 revealed Titan, Saturn's moon, and as an Earth-like world in terms of having lakes, rivers, and weather phenomena, aiding understanding of Earth-like planetary processes beyond exoplanets. So what is it, K218? K218 is an M3V red dwarf star, smaller and cooler than the Sun, with about 45% of the Sun's radius and a temperature around 3,457 K. The star is moderately active and about 2.4 to 3 billion years old. To date, thousands of exoplanets have been confirmed overall, and a significant fraction of these orbit red dwarf stars. Specifically, we can say that the HARP survey of 102 red dwarf stars found 9 super-Earths, including some inhabitable zones, and estimates that about 41% of red dwarfs have super-Earth planets in their habitable zones, and more than almost 5,800 exoplanets have been confirmed in total, with many orbiting red dwarf stars, though only about 20 massive exoplanets have been detected around M-type red dwarfs specifically. So the recent discoveries include 4 confirmed mini-Earth exoplanets orbiting Barnard's star, a nearby red dwarf, highlighting ongoing detections of smaller rocky planets around such stars, and the Kepler Space Telescope has discovered several tens of planets around red dwarfs using the transit method. While exact totals vary depending on detection methods and ongoing confirmations, it is clear that thousands of exoplanets have been confirmed orbiting red dwarf stars, with many being Earth-sized or even super-Earth-sized planets, including those in habitable zones. In summary, I can say that the confirmed number of exoplanets orbiting red dwarfs is in the thousands, with ongoing surveys continuing to increase this count steadily. So, red dwarfs, it's actually it's common. Frequently they host exoplanets, especially Earth-sized and super Earth-sized planets, and observations indicate that about 40% of red dwarfs have a super Earth class planet orbiting in their habitable zone where liquid water could exist. Let's say, for instance, the TRAPPIST-1 system, a well-known red dwarf about 39 light-years away, has 7 Earth-sized planets orbiting it. That's insane. And the Speculoos project discovered an Earth-sized planet named Speculoos 3b orbiting an ultra-cool red dwarf star about 55 light-years away. This planet is tidally locked and completes an orbit in just 17 hours. Also, surveys combining data from instruments like HARPS and UVIS show that virtually all red dwarfs have at least one planet, with many orbiting within distances that could allow habitability. Other notable red dwarf planetary systems include Gliese 581 with multiple planets, including some in the habitable zone, and TOI 1231b, a Neptune-like planet orbiting a red dwarf about 90 light-years away. While large Jupiter-sized planets are rare around red dwarfs, smaller rocky planets and Neptune-mass planets are very common, and despite challenges such as tidal locking and stellar activity that may affect habitability, red dwarf systems remain prime targets in the search for potential habitable exoplanets. And what are red dwarfs anyway? Well, red dwarfs are the smallest and coolest type of stars on the main sequence, typically with masses less than about half of the Sun and surface temperatures ranging roughly from 2 to 4,000 Kelvin. They fuse hydrogen into helium with the proton-proton chain reaction at a slow rate, which results in very low luminosity, sometimes as little as 1/10,000th the brightness of the Sun. Their small size and low temperature give them a distinct red color, and red dwarfs are fully convective, allowing them to burn a large fraction of their hydrogen fuel and granting them extremely long lifespans, from tens of billions to potentially trillions of years. That's crazy. Well, in terms of abundance, red dwarfs are by far the most common type of stars in the Milky Way galaxy. They make up about 70 to 75% of all fusing stars dominating the stellar population. And estimates based on observations and modeling suggest that there are approximately 58 billion red dwarf stars in our galaxy. About 7% of these reside in the galactic halo, with the rest distributed mainly in the galactic disk. Because of their low brightness, red dwarfs are difficult to observe individually from Earth without telescopes, but they are the most numerous stars near the Sun, including Proxima Centauri, the closest star to our solar system. And today, we still don't know if DMS is or dimethyl sulfide is it a guarantee, for life? Although the James Webb Telescope provides unprecedented sensitivity and a wide wavelength range, the initial detections of molecules like methane, carbon dioxide, and possible biosignatures were based on just a few transit observations. So this limited data can lead to ambiguous or low confidence detections. For example, the early James Webb data give precision comparable to multiple Hubble observations, but still require more transits to confirm findings robustly. Some analysis also suggests that the identification of DMS and related molecules results from model assumptions that restrict possible atmospheric compositions, potentially biasing results. Independent reanalysis found that the data do not strongly exclude the absence of these molecules, with detection confidence around only 1 sigma, about a 28% chance of no detection, indicating weak statistical significance. So it's the research is still going on. I guess we will have more info next year, this time next year, whatever you want. But we'll see. It's like the research never ends, and the number of planets discovered in so-called Goldilocks zone is astonishing and rising. It's exponential, I guess. But then again, it's a vicious circle. When we keep reimagining things like we actually know what we are looking for, instead nothing can be further from the truth. And if I could take a wild guess, I would say that when it actually happens, when we really will be sure about life, I guess it's going to be by accident and totally not what we were looking for. Hope to live to see to see it, but numbers are, you guessed it, astronomical. So I will rather enjoy my tea and watch Odyssey 2001 for who knows what time again. So if you want to dig more on the subject, there's always more. Sarah Horst, associate professor at Johns Hopkins University, is a planetary scientist recognized for her pioneering work on photochemical haze formation in planetary atmospheres, including those of exoplanets Titan and early Earth. She has developed laboratory experiments simulating atmospheric chemistry to understand how haze particles form and affect observations of exoplanet atmospheres. And also astrophysicist Eddie Schwitterman, an assistant professor of astrobiology in the Department of Earth and Planetary Sciences at the University of California, who is also an astrophysicist specializing in the study of exoplanet biosignatures, remotely detectable signs of life on planets beyond our solar system. And his research focuses on identifying atmospheric gases and surface features that could indicate biological activity, assessing their detectability with current and future telescopes, and understanding potential false positives from abiotic processes. Abiotic, yeah, okay. Together, they emphasize the need to rule out abiotic processes and gather more data. So follow up James Webb observations using MIRI and plan for 2026 to confirm the signal. So. Instead of conclusion, I just want to say that next time, maybe we should select another candidate, like some other planet. Well, until then, probably far away in the future, you know what to do. Select your star. Stay selective. Bye-bye.